Good morning, champs. Let's understand plug flow's reactors. So unlike the other reactors we have seen before, there is no stirring within the plug flow reactor. This means that we will have a radial change of the concentration of a species I within the reactor. So on the left side of our reactor, we would have our entering molar flow rate, which consists of a volumetric flow rate and a concentration, let's name it Ci0. On the right side of our reactor, we would have our leaving molar flow rate. So we would still have the same volumetric flow rate, however, our concentration would change to Ci out. So to determine the radial change of the concentration, we first need to take a look into a segment of our plug flow reactor, which consists of a thickness of dc. So let's take a closer look into the segment we just cut. So our segment will look something like this. So the segment consists of a cross-section area named A, which is the same of the reactors. So this is the same area. So it will consist of the volume dV at the given dc. Hence, dV will result in A times dc. So on the left side of our segment, there's a molar flow rate, which consists of the volumetric flow rate, V, and the concentration of the species I at the position C. So let's say this is the position C, and exiting our segment is the position C plus dc. And leaving our segment, we would have the volumetric flow rate V and the concentration of the species I at the position C plus dc. And within our segment, we would also have our reaction taking place. So we have to consider the reaction rate of the species I. So let's proceed with a species balance of the species I in our segment. So the change of the species I with respect to time is going to be equal to the entering molar flow rate, which is Fi at position C, minus the molar flow rate which leaves our segment, which is Fi C plus dc, plus the reaction rate of the species I, times the volume of the segment, which is dV. So for the plug flow reactor, we assume steady state. So that means that the change of species I with respect to time is going to be equal to 0. And if we consider that the molar flow rate of a species I is equal to the volumetric flow rate V times the concentration of the species I, and considering steady state, the left side of our equation is going to be 0. So 0 is equal, and we insert the molar flow rate equation on the right side we have. So we can say that volumetric flow rate times the concentration of the species I at position C minus the volumetric flow rate times the concentration of species I at position C plus dc plus the reaction rate of the species I times dV. So on the following step, we will factor out our volumetric flow rate V. So V, and in parentheses, C minus Ci at position C plus dc plus reaction rate of the species I times dV. So this term, for this term we will use Taylor expansion. So we will say that the concentration of the species I at position C plus dc, so using first order Taylor polynomials, we will say that this is equal to Ci at position C plus dci divided dc times dc. So this we will insert in our equation. So V times Ci at position C minus CIC minus dci divided dc times dc plus Ri times dV. So these two cancel out. So this will result in 0 being equal to negative the volumetric flow rate times dci divided dc times dc plus the reaction rate of the species I, Ri. And for dV, we will use this term we just discussed. So Ri times A times dc. And the reason why we replace this term with this one is to get rid of the dc term. So now we divide our equation with dc. So the dc terms will result in 1. And in the next step, we're going to sum the equation with V times dci divided dc. So V dci divided dc is going to be equal to Ri times A. So this might seem a little bit trivial, but what we wanted to do is we want to divide the equation with V. So dci divided dc is going to be equal to 1 divided the volumetric flow rate times Ri times A. So now we are going to separate the variable, meaning that we want to have dci in one side of the equation and dc on the other side of the equation. So the reaction rate of the species I depends on the concentration of the species I. Not always, because for zero order kinetics this is not the case, but for almost all cases. So first we separate the variable, as I just said. This we do by multiplying the equation with dc. And to put our I together with the dci terms, we have to divide the equation with our I. So dci divided the reaction rate of the species I is going to be equal to 1 divided the volumetric flow rate V times A times dc. So what we are going to do now is we're going to integrate the left side from the entering concentration in our plug flow reactor, which we named Ci0. And on the upper boundary, we have the concentration leaving our system, which is Ci out. And on the right side of the equation, we will integrate it with respect to the length of the plug flow reactor. So at the position C0 is where it starts, and the upper boundary of our integral is going to be the length at C equal L. We will name the length of our plug flow reactor L. So the integral from ci0 until ci out dci divided ri. So the volumetric flow rate and the cross-section area will not depend on the position C. They will be equal at each position C, so we can bring it in front of our integral. So 1 divided v times a times the integral from 0 to L dc. And this is going to be equal to 1 divided v times a. And since we're integrating over dc, we just have to take the limits into the consideration, and this integral would result in L minus 0, but we just write down L. And the cross-section times the length of the plug flow reactor is actually the volume, as it's defined as, well, the cross-section of the reactor times the length. So this will result in the volume of the plug flow reactor divided the volumetric flow rate. And this is equal to the mean residence times tau. So in some textbooks, I have seen use the term Tm, but here we will just stick to tau. So for a plug flow reactor, we can say that the integral from the entering concentration till the exiting concentration of dci divided Ri is going to be equal to the mean residence time. So let's represent this in a more graphical manner. So on the y-axis we have 1 divided the reaction rate of the species I, and on the x-axis we have the concentration of the species I. And let's say we have determined this correlation experimentally, and let's say the correlation can be sketched as following. So, and if we have a process where we have the concentration of the species I0 entering our plug flow reactor, and we want to have a concentration of the species I leaving our reactor, we would need to dimension our plug flow reactor, so tau would be equal to the integral of this curve, which is tau. So on a separate note, let's say we have a reactant A reacting with the rate constant K to our product P. So we can say that the reaction rate of the species A, assuming elementary reactions, is going to be negative the rate constant K times the concentration of the species A. So in previous videos I have solved many examples, especially for elementary reactions, and I really encourage you to watch them, because for this case it's pretty easy, but yeah, it can be more complicated, as you would find out in my previous videos. So if we would have a plug flow reactor, we apply the formula I just derived. So let's name our entering concentration Ca0 and the exiting concentration just Ca of dCA divided the reaction rate of the species A, which in this case is negative the rate constant K times Ca. And this is going to be equal to tau. And we can bring the 1 divided negative K in front of the integral, as this will not depend on Ca. So now we have the C integral dCA divided Ca being equal to tau. So as a reminder, the integral from a lower boundary xl and an upper boundary xu of 1 divided x dx will result in the natural logarithm of x, where we insert the upper and lower boundaries, resulting in ln upper boundary xu minus ln lower boundary xl. And if we apply logarithmic rules, this is going to be equal to ln of xu divided xl. So let's apply this here for CA. So this is going to be equal to ln concentration of the species A, where the upper boundary is CA and my lower boundary is CA0. And this is going to be equal to tau. And yeah, let's apply the logarithmic rule here. And let's also multiply this equation with negative k to bring this on the right side of the equation. So ln of CA divided CA0 is going to be equal to negative k times tau. So CA divided CA0 is going to be equal to E elevated negative k times tau. So our concentration exiting our plug flow reactor CA will result in CA0 times E elevated negative k times tau.